欢迎参加本次的网络研讨会。影片中将展示如何使用 ARM Keil 工具和 ARM Virtual Hardware， 将从本地端开发的工作转向云端。这是今天的议程。首先，我会说明如何将 Keil MDK 和 CI/CD 开发流程对接。然后，我会展示一个基于 MDK 开发的 project， 包含两个不同的硬体目标，一个是虚拟硬件，另一个是 NSP IMSRT 1050 EVKB 的开发版。一旦确认这两个项目在 MDK 中都能如预期的运行，就会切换到使用 Python Script 的 Local Build， 以验证 AVH 项目在 MLNDK 的情况下也能正常运行。接下来会使用 Python Module 来检查 Project 是否在 AWS Machine Instance， 也就是 AMI 上运行。最后，我将所有的内容推送到 GitHub， 并检查工作流程是否在 GitHub Action 上运行。这次网络研讨会将不会深入探讨 ARM Virtual Hardware 的细节，本系列的其他网络研讨会已经对此进行了解释。若您还未了解 ARM Keil MDK， 尤其是如何创建、建构以及运行专案，建议您可以观看我们的一些入门课程。最后，本次不会详细说明如何在 AWS 上创建一个与 AMI 共同使用的凭证， AVH 文件中已经对此进行了解释。现在让我们开始吧。ARM Keil MDK 是一种在您的 PC 上本地端运行的 ID 开发环境，其中包括针对 Project 所需要的创建、构建和出错等一切的功能。它还包含了可用于验证程式的 ARM Virtual Hardware 虚拟目标。等到了手边有了实际的硬体之后，就可以在电路板上运行相同的程式，并且开始出错。现在，许多的开发人员使用 repository 进行协作开发。这个 repository 也是 CI/CD 工作流程中的资料节点处。您可以在公司内部网络的机器上进行本地端的运行，我们称之为内部部署或者 on-premises， 或者您可以在外部网络使用 GitHub 等服务。所有的资料都会在私人 repo 中进行。在这里，您可以针对使用者做资料存取管理的管控。您的 project 不会因此而被公开在外部网络上。在云端的 CI/CD 的环境中，您使用 AWS Machine Instance 或称为 AMI 来访问 ARM 编译器、构建工具以及 AVH 模型，用来运行您在 Print 上执行的相同测试。透过增减在云端的 AMI 的数量，您可以选择是否加快执行速度。AMI 和并行构建的数量取决于您 project 可需用的资金，因此您可以在需要的时候透过增加更多的机器的能力来加快开发的时间。完成项目之后，您可以再减少并行 CI/CD 运行所需要的 AMI 数量，用以降低成本。这就是使用云端 CI/CD 流程最大的诱因。在切换到 demo 之前，以下是将 project 移动到云端的标准流程。首先，在 MDK 中创建 project， 并验证它是否如预期的建构以及运行。其次，使用 Python Script 检查 CI 流程，使用 Python Module 检查 AMI 流程。第三，使用相同的 Module 在 GitHub 上运行 project， 并使用 GitHub Action 在云端运行 CI/CD 的工作流程。Unity 是一个专门为 Embedded C 创建的单元测试框架，它是用 ANSI 所编写的，可以使用任何的编译器建构，并包含大量不同的 assertion 来满足您的需求。在此范例中，我们会使用 test assert equal int 来检查函数调用的结果是否符合预期。例如，测试程式会在检查1加-1是否等于2的时候会回传 fail。Unity 是用原生的 C 所编写的，速度非常快，并且可以在 MDK 中轻松的使用，因为我们已经用它来创建了 CMC Spec。只需要在您的 project 中添加软体组件，并在您的代码中使用通用的 assertion function。让我们看一下 demo， 以了解它在现实生活中的案例是如何工作的。
I have opened the project from my GitHub repo, and it shows the README MD file, which gives explanation of the setup of the overall project and how to set up your environment and how to run it in MDK and locally. So this is all available in the README MD file. And as we can see here, it has basically two targets. It's the CMSDK CM7 VHT and the IMXRT 1050 EVKB. The reason why I'm using a CM7 virtual hardware target is, of course, because the 1050 is a Cortex M7 based device, and I want to have it, well, as close as possible, the simulation, to the real hardware. Let me open the main.c file and zoom in a bit. So we can see here, it's a standard main.c file with some ifdefs. Of course, I cannot use 100% the same code because the real hardware behaves a little bit differently than the virtual hardware target. So for example, the UART pins, I don't have them in the virtual hardware target. I don't need to have them here. And also the whole board setup section is not available. So I have covered that with an ifdef. And but for the virtual hardware target, I have a standard IO init function. And here's the actual function that I'm going to check. It's a sum function, basically has two parameters, a and b, and returns a plus b. And then I have the unit tests, setup and teardown. That's basic functions from Unity. I don't have anything in there. I don't need to set up anything. And then I have the actual tests. So test my sum positive. So testing a positive sum, I add 1 to 1. I expect 2. Here's negative. I basically add -1 to -1. I expect -2. Sum of zeros. And here's the failing test case where I add to the 1. I add a -1. And here basically the expectation is wrong because it's set to 2. It of course need to be 0, but we will see that how the test case fails in that case. And then again, in the main function, there are again a couple of setup things that I only need for the real hardware. Here I need the standard IO init. I have some printf debug message at the beginning of the Unity tests. I run then all these 4 tests and basically have an end. Let's take a look at the software components used in that example. So I move that up here. I'm using the compiler component, especially for redirecting the standard output to a user-based file, which I will show in a minute. In the hardware target, so the actual hardware target, the IMXRT, I'm using exactly the same setup. Apart from that, here's the Unity software component added to the project, and apart from that, it's nothing special. A couple of drivers for the USART, for example, SEMSys core files, of course, and some board support file for this virtual board based on the MPS2. So let me open this retarget section here. We see we have 2 retarget files. This one is currently not used because that's the one from the IMX 1050. This is the retarget for the standard IO of the virtual hardware target. So it's again, the retargeting logic or code is different between the virtual target and the actual hardware, but that should not make big of a difference. So let's quickly, or before building the project, let's take a look at the setup here. How the debug is set up. So I'm using the model's Cortex M debugger. If I click on settings, I see I use the executable for the Cortex M7. I'm using the Cortex M7 core in there, and I have a configuration text file, which click on edit. It opens then in the background. Just say, okay, we can take a look here. So it opens a telnet terminal, basically. In that case, or in this case here, I'm using PuTTY because I have saved a special configuration in PuTTY. The printf debug output is lacking the carriage return. So if you don't have that specific setup, then it looks a bit awkward. The output with this call here to PuTTY with a special setup we will see it's nicely formatted, but that's just a minor thing. So let's build this one here. Okay, that finished quickly. And now I go to debug mode. And here we see a couple of windows that are opening in the background. So I'm calling the virtual hardware target executable. This is a special window from the board. And now I'm in the debug view of Keil MDK. So I stop at main. That's the usual thing that happens. The program is loaded and execution stops, or it runs until main and it stops there. So kind of a breakpoint. And if I press the run button, a putty window opens and we see the unit tests, and this test my sum fails because expected was 2 and the actual result was 0. As we thought, the project fails because the expectation was wrong. So this is basically how the simulation works. Now let's stop the debug session here, and we basically switch the target to the IMXRT. I have attached the board already to my PC. I can verify that. If I go to debug here, I'm using the onboard SemSysDApp debugger. If I click on settings, I see that it is enabled. I see a core site unit connected here, so everything is fine. The connection is okay. I hit OK here as well. And I basically build the project here. A couple of files are changed. And I go to debug. The file is loaded into Flash. So we have a Flash download here. The target is flashed. And again, it runs until main and stops there. Now, let me bring up another putty window, and I will just add that here and use that one. So if I now hit on run, we have exactly the same output: pass, pass, fail, pass. So we have verified that the simulation is running in on the virtual hardware target, and it is also running on the actual hardware, and the simulation result is the same as the result on the actual hardware. So this basically is already it for the MDK part. Again, we have a project with two different targets, with the virtual hardware target that is using the same processor core as the actual hardware that I have connected to my PC. So this is running fine. And now we can start to move this project to the cloud. Actually, there's one final step that we need to do. We need to save the project of the AVH in a format that we can use further on in our command line tools. And so I go to Project, Export, and I export and I save the project as CPRJ format. So CPRJ format is the native C project format from the SemSys build tools, and we will be using that in the following steps, running locally on the CLI, but also when we run on AWS. We're now at the second step. I will use the build.py Python script to check the CLI flow, and afterwards the AVH client to check the AMI flow locally, and later I will use the AVH client to run really on an Amazon machine instance, and finally wrap everything up in the GitHub action. So building locally, I have opened a terminal here. I'm using the Git for Windows bash that comes with the Git installation on my Windows machine. And the first thing that I need to do is basically sourcing some files. I need to source the setup of the SemSys build toolbox, etc the setup, which basically adds a couple of paths to my path variable. And I switch to the directory where everything happens. This is Chris from local to cloud. Let's take a look at the content of the directory. I use the dir here, and we see we have the basic CMSDK CM7 VHT C project in there, which I had only generated just now. The Microvision project files, UVGUIX, Optex, and projects, the build Python script, and then some subdirectories for the CMSDK and for the IMXRT, the main C and header file configuration for MDK for the VHT. We have a separate configuration that I will use later when not running with MDK. And here's a requirements.txt file, and if I check that requirements text file, it tells me what I need to install in Python. So I need the Python matrix runner and the JUnit XML. These are two packages, Python packages that I need to have in my installation. So I go pip install -r and I give them the requirements text file. In my case, nothing will happen. I have already installed them, but just to make sure you have all the steps that are required. So you see a requirement already satisfied. Everything is fine. We have installed those dependencies. And now I can actually start using the build Py script. And this build Py script has different options, and I start obviously with build. I of course need to build the project, so it's now executing the cbuild shell script, which is part of the SEMSys toolbox, with the cprj project format file that we have just created. Succeeded with exit code 0, so everything is fine. The matrix summary gives us a success for the build. And after that, I run the project. And here you see it executes the VHT with the configuration file specifically for the VHT simulation. These messages about subprocesses not terminating, this is a kind of Windows problem. My telnet terminal window was not exited on time, so the simulation thinks it was not terminated. I just saw it popping up just quickly, and now it's basically closed again, so everything is fine. But this is quite important if you run an AMI container, for example, to make sure that everything is working as expected. And now I can check my report. So in the 24x unit, we see the test cases that have been run. And as expected, test my sum failed with, again, the message expected to was 0. So using this locally here works well with the build Py script. So what is actually in that build Py script? I have it open here. As I said before, when talking about the requirements text file and the packages that you need to install, it is using the Python matrix runner package. And I jump over the beginning here, nothing fancy. The Unity report, this class is implemented as a report filter so that it later can be used in a test report chain. The relevant part here is the stream property that receives a data stream, standard output of the model, so what we normally have from in the telnet window, for example, and translates it into JUnit format. This is done by pattern matching using a regular expression on the expected Unity framework output. And each found test case is then, with this result, converted into a JUnit XML test case taken from the Python package JUnit XML. That's what happens here. The Python matrix runner has built-in support for build configurations. This example has only one axis called target with one value called debug, and more elaborated use cases may add further axes for support of different compilers, optimization levels, target devices, whatever. So in this case, we have just one target. It's the CM SDK CM7 VHT. The matrix action. Here we have basically two actions. We have the build action, as said before, and the run action. So the build script offers these different top-level actions, which I have triggered from the command line. Each action is defined by an according method. An action method must at least yield one shell command to be executed. Complex actions can be composed from multiple shell commands, interleaved with additional Python code. So it's very flexible. In this basic example, additional Python code is used for some processing of the shell command results, such as creating a zip file from the build output. And finally, we have the matrix command run cbuild and run VHT. And if we scroll up a bit, we see the run VHT is used in the matrix action run. So each shell command is required to compose the actions and is defined by a method returning an array with the command line parts. A command can be further customized, for instance, by attaching a test report. The test report is created by applying a chain of report filers to the output of the command. In the basic example, the output of the virtual hardware target model is captured. In the console report, the Unity output between the known test markers is cropped, crop report, and the remaining data is converted into JUnit format with the Unity report. So this is what happens here in this build Py script. The good thing is you can just use it as is. It's already pre-configured for this example. So if you would like to use a different model, for example, you just change the axis. So you could say for debug, I'm using CM SDK CM4 _ VHT, for example. Next, in the flow, I use the AVH client, which is a Python module, to verify that the process is working locally and finally in the cloud on an AMI instance. This Python module provides an interface for deploying and using ARM virtual hardware. It enables uniform implementation of CI operations and supports many different environments such as Jenkins, GitHub Actions, or local use with AVH targets as we are using here. So how is this client working? It basically reads a YAML file that contains the steps that will be executed in the flow. The client has basically two operation modes. One is local, the other one is AWS. And when you run it locally, it uses the backend on your local machine, which means that it executes the locally installed VHTs. The AVH client copies the workspace into this backend and runs the build Py script. Once finished, it extracts all artifacts that we are interested in keeping. In this picture, the executable, for example, but you can specify any files that you want to keep. When run in AWS mode, the same flow is followed, only that it creates an AMI and runs the flow directly on that instance. Once finished, you know that the whole flow should also work when you run in the cloud on GitHub or in a Jenkins CI pipeline or whatever is supported by the AVH client. Okay, now I'm back at my console in my working directory, and the first thing that I need to do is install the AVH client. As before, I have done this already, and it will give me the message that nothing has to be done. But again, for the sake of completeness, I show you this step here. So you see requirement already satisfied, everything is fine. And I start by executing the client locally. And here I need to specify the -b local because the default is -b AWS. So if I don't specify -b, it will use AWS. I want to run everything locally. And we see, yeah, these are the files that are uploaded. It's executing the pip install, which is already satisfied. The cbuild shell is run to create the project. That's the output of the build run, and here's the simulation. And the tests failed because we had one failure, just as we had that before. But we know, okay, AVH client is working with this package locally, and now I start using an AWS machine instance or AMI. For that, I have to source some secrets, my credentials. I will show you this file later. So this basically has just an export of the secrets so that they are known to this console. And now I can basically run the AVH client on AWS. But it's always good, especially when you are in an early development phase, that you do the following. You say -- instance name and call your instance whatever you like and say prepare. With this, you create or you prepare an instance that can then easily be reused again. If you don't do that, it always prepares a new instance when you run it. And this takes a couple of minutes. Here in this webinar, I will cut that out, but it takes about 5 to 6 minutes just to create this instance. If you create it once, you can then always execute on it, and that just takes a minute or so. So it's much faster if you prepare your instance in advance. Okay, it has ended. So we have prepared the instance, and now we can basically execute on the instance. So I just run now instead of prepare. I say execute. And now the script does everything that it did before, just directly on the EC2 instance. So it creates the workspace with all these files, moves it into the cloud or onto the AMI, and then the AMI executes the build py script and tearing down the instance. So that's it. And now one good advice, we have created this instance now manually. So we prepared it manually and it's now available. Usually what the AVH client or with the script does is that it initiates the instance again, runs everything, and then stops the instance. Depending on what you're doing, how you are doing, when you are doing it, it might not stop. And this, of course, means that it continues to ask for coins to be inserted. So to be very sure that you are not billed furthermore, you can now basically clean up everything. So this means that the instance will be killed. Okay, done. So now before I go to the last step and show how to move to the GitHub, let's take a quick look at this credentials file that I was talking about. So I have it open here, credentials.sh. It's basically exporting a couple of secrets to the console. So these secrets are required to run the AMI. As said, I don't explain in this webinar how to set up these secrets in your Amazon account. That's something that you can do on your own. There's lots of documentation about this, how to get this started. But just so much, we will use these credentials in the next step on GitHub as well to run the action on the AMI. Back to the console. I said it in the beginning, we see from the path here. This is a Git directory or a Git repository. We're in the main branch. I just check the status. And there are a couple of changed files. So I basically will add those files. and then I will commit. It's opening the editor for the commit message, and I just say updates for the cloud workflow. I save and close. And then I finally just push it. So this basically should be it. Let's take a look here. When was the last commit? Just a minute ago. So this is my repo in the cloud. And I can already check my workflows, my GitHub actions, because I have already a workflow file there. And here we say updates for the cloud workflow. I click on that, take a look at CI test. And again, this will also take a couple of minutes, because here, as I said before, for the AVH client, a new instance of the AMI will be created, which takes a couple of minutes. But once this is finished, the flow will run and the build py script will be executed, and we will see basically the same outputs as locally. I will again fast forward here. Okay, the job has completed, and maybe we can, or I will review here, especially the run test part, where we see that, the workspace is uploaded and build process is done here. Successfully built and run 3 of 4. So everything that we have seen before in the build py script or in the AVH client locally. So everything is done correctly. Also the results have been archived. And the job has been completed. And if we go to here, the summary again, we see that the last push, it took 7 minutes 19, and that it was successful with this green mark. And that's it. Now, every time you change something, and we can quickly simulate that here by, for example, just going to the main.c file and editing this here. And I just add a comment, new comment, and I commit the changes. I go to the Actions tab and I see that update main, a new run has just started. It will take again 7 minutes. So I think you get it. Let me show you the workflow file to establish this here, this workflow. It's under .github workflows. It's called basic YAML. Again, another YAML file. Let me zoom here. Okay. So we see we need a couple of secrets. I will show you in a minute. And then we start with on push or pull. It does something. It uses the environment variables that I have as GitHub secrets. And then it starts the CI tests. It tells me what kind of machine it is. It's an Ubuntu latest. And we have a couple of actions that start here, checking out the code, setting up Python 3. And then we install the AVH client. So this is everything after this is basically expected already, or we know already. Pip install AVH client. Then we run the test with AVH client -b AWS execute with the specified file, the avh.yaml file. And finally, we archive the results. So this is a very elegant way to set up such a workflow script. And I was talking about the credentials. So here under settings, we have here in the security part, we have secrets and actions. And we see that there are a couple of repository secrets all the secrets that I had specified previously as well. And yeah, I updated them a couple of days ago. Nice thing about this here is you can, with this button, you say new repository secret, and you can add a new secret. But once you have added this, it's not readable anymore. So here in this list, you can either update it and add a new secret, or let's say the content of the secret, change the content of the secret, or you can remove the secret completely, but you won't be able to read out the secret anymore. That's hidden somewhere on GitHub servers. So it's safe to use with the GitHub action. Before I get to the summary of this webinar, let me quickly show you a real-life example, because this example that I've used in my webinar here is of course a very, very simple one, but you can use that for much more complex things. I have opened here another GitHub repo from ARM Software. It's the SEMSys RTOS2 validation repository. It's a test suite to validate SEMSys RTOS2 implementations, and we are using this to verify our own Keil RTX and the SEMSys FreeRTOS implementation that we have created against the RTOS API. And if you take a look down here, you see the test matrix, and this is what we had in the basic.py script, this matrix runner. Here you can see that we have a very, very complex test matrix. We have two different compilers, ARM compiler 6 and GCC. We are using all kinds of different devices, starting from M0 Plus up until I think currently it's M55. Yeah, the SSE 300 is basically M55, and then on two different RTOSes. So you see the list is quite extensive. And yeah, with this approach, we can of course run lots of actions. We have also two different runners here, one just for publishing the documentation and one which is the actual validation running on the hardware. If I take a look at the last workflow run, we see that there are 50 errors, which is basically expected with such a big matrix. It's not 100% perfect. Let me take a look here at the run, and I go to run tests. This is a very, very, very long list. And I just go to the end and I go back up again. Here we see this matrix summary, basically from all the matrix tests. And we see that not all runs have finished. For the first one, 158 from 159. For FreeRTOS, we have less tests. It's 125 from 138. And so you see this is why we get the 50 problems or 50 errors. But what you can see from here is that this matrix summary is really coming in handy, giving us a clear result table that we can use to check our results.
从一开始使用 MDK 在实际的硬体上以及虚拟硬体上所做的本地端开发，我们已经成功的将 project 移转到云端上使用 AMI 以及 GitHub Action 来做开发。现在，开发人员可以开始向这个 repository 提交新的 workflow。在最后一张 slide 中，您可以看到关于 Keil MDK 虚拟硬体的更多的讯息文件，还有网络研讨会范例等等。它是一个 public repo， 因此您可以在任何地方连接到以上的网址。